So in this video, we're going to develop the basic hydrostatic equation. So this equation will be the starting point for every problem that we do in fluid statics, including manometer problems that we're going to look at in this module. So the basic hydrostatic equation will tell us how the pressure changes as we move from point to point in a fluid that is in a hydrostatic state. So that's what it's used for. It's used to calculate the pressure field in fluid statics. So how does the pressure change as we move around in the fluid? That's always going to come from the basic hydrostatic equation. Now we need to understand that the basic hydrostatic equation will only apply if the fluid is in a hydrostatic state. And we'll see why that is as we go through this development. So let's start off by considering any static fluid in a gravitational field. So all of the problems that we're going to do are going to be on Earth, so we need to have a gravitational field because it affects the pressure distribution in the fluid. So we're going to define here our coordinate system that we're going to use for this development. And so we have a Cartesian XYZ coordinate system here. When we do problems in fluid statics, occasionally we'll be using other coordinate systems, but we can develop the basic hydrostatic equation in the context of this coordinate system. It actually would work in any coordinate system, as we'll see when we start to use it in example problems. So we have our Cartesian XYZ coordinate system there. And I don't show the unit vectors here, but remember we have an I hat unit vector in the X direction, a J hat unit vector in the Y direction, and a K hat unit vector in the Z direction as well. Now the other thing we're showing here is the acceleration due to gravity. So here I've shown it in the negative Z direction. So the symbol that we're going to be using for the acceleration due to gravity is G with an arrow on top indicating it's a vector. Realize that this is just one possible orientation. G can be in any orientation relative to our coordinate system. One of the things we'll see when we start to do problems in fluid statics is we'll want to choose a coordinate system and the orientation of the coordinate system to make doing that particular problem easier. So we'll talk a lot about that when we're doing problems. Now I'm just having G in the negative Z direction as an illustration. So we're going to study a very small differential volume of fluid. So we have our coordinate system here. We have our acceleration due to gravity in that direction. This is an extremely small or differential volume of fluid, just a very, very tiny cube. So its dimensions line up with the coordinate system here. So it's dx in this direction, dy in that direction, and dz in that direction, a differential volume. Now the pressure is what we're interested in here. So the pressure in the very center of this small cube is P. So whatever value that is, that's what we're going to be figuring out in different applications. But that's P at a particular location XYZ in this fluid. So the location of the center of this volume has some XYZ coordinates, and the pressure at the center is known as P as a function of X, Y, and Z. So that's the pressure at the center of the differential volume. And we'll see that that pressure plays a role in figuring out what the forces are on this differential volume a little bit later on. But the reason we bring it up now, the whole purpose of the basic hydrostatic equation is going to be to tell us what this pressure distribution is. So we're just defining our notation for that right now. So what we're going to do here is apply Newton's second law to that differential volume. So we're going to apply F equals ma to our small volume dV. Now just a few points about notation here. One of the things about fluid mechanics is the letter V is used for two different things: volume and velocity. And that can get confusing, so you need to pay attention to that. Now, as you get more experience with these equations, you should be able to recognize which V is which by the context. So what the equation is doing, what it's talking about. You should be able to tell whether the V is volume or velocity. Now, I'm going to try and help a little bit with that in this section of the course. When I'm talking about V being a volume, I'm going to put a tilde on top of it here. So that little symbol there is to help remind us that this V is talking about volume. Notice that is not a vector of any kind. It's not an arrow or a circumflex. That's just an indication that this V is a volume. So that's what I'm talking about there. Now, vector quantities, of course, the traditional way is put an arrow on top of them, and that's what we're going to do here. So force is a vector, acceleration is a vector, and mass, of course, is a scalar. So even though this is fluid statics, we're not saying here that the sum of forces is equal to 0. We're saying it's equal to mass times acceleration. Remember, in fluid statics, we can have situations where the fluid is accelerating, as long as there's no relative motion between any two fluid particles. So we need to keep the ma on the right-hand side of Newton's second law here in order to properly handle those situations. Now, because we're applying this to a differential volume, a very small volume, we'll actually write this as dF, a very, very small force, is equal to dm, a very, very small mass, times its resulting acceleration. And notice the left-hand side here, we're talking really about a sum of all of the forces acting on that dV. I haven't shown the summation sign here. So we're going to concentrate on the left-hand side of this equation for a little while. We're going to ask ourselves, what are all of the forces that can act on this small element of fluid? Well, the first thing we do is we break those forces down into two types of forces: body forces and surface forces. And that's indicated by this extra subscript B and S there. So we're going to start off by looking at the body forces, and then we'll move on to the surface forces, and we'll come back and add them together, and we'll have the left-hand side here of Newton's second law. So first of all, body forces. Well, a body force is a force that acts on the fluid within our differential volume. So every particle or every atom of fluid inside of the volume can have a body force acting on it. Well, what is the source of these body forces? Well, there are really only two, and that is gravity and magnetic field. Now, essentially every one of the problems that we're going to look at, gravity is going to be at play. So the weight of the fluid inside of that differential volume is always going to be important in the problems that we're going to do. And essentially magnetic field is never going to be important. There are some very specialized applications where if we have a conducting fluid and it's moving in a magnetic field, then there can be an additional body force because there's magnetic forces acting on every particle of fluid inside of our differential volume. But we're certainly not going to look at any of those applications in this course. So gravity, or the weight of the fluid, is the only body force that we need to worry about. So we need to quantify that body force. So the body force, and again, let's understand all of the notation on the left-hand side of this equation. F is a force, and we're reminding ourselves that that's a vector, so the direction is important. Because we're talking about forces and accelerations, we need to get the direction of everything correct, or this equation is not going to work for us. So force is a vector. We're talking about a body force, so we have a subscript B, and we're talking about a differential force, so just a very small force because we're focusing on a very small control volume, just that little differential mass. So what is that equal to? Well, a body force, or weight, is just equal to mass times g. So the mass is dm, again because it's a small differential mass, and the acceleration of gravity that we defined is g. And again, that's the vector quantity. So the thing that gives this its direction is the direction of g. So when we go back and reassemble our sum of forces equal to mass times acceleration, the body force is going to be represented by this. Now, before we do that, or before we move on to the surface forces, we're going to expand on this dm a little bit. So the mass is equal to the density times the volume. So dV is the volume of our little cube, rho is the density of the fluid, so the product of those is dm. And we're going to further expand this just getting it ready to be substituted back into our sum of forces, we're going to expand dv and call it dx, dy, dz. So the product of the length of the three sides of our cube is going to be the volume. So density times volume times g gives the weight or the body force of that fluid. Now we'll see later on why I've expanded these things out into this much longer expression, and it's because some things are going to cancel out of the equation. But we're just going to set this aside for now and move on and consider the surface forces next. So a surface force is a force that acts on the surface of our dv. So the 6 faces of this cube are going to have forces exerted on them from the fluid that is outside of the cube. So whatever's happening outside of this cube could be exerting forces on the 6 faces of this cube. So we want to think a little bit about the nature of those forces, and we're going to concentrate on this face right here just as an example. Well, one thing that could be happening is there could be shear forces exerted on the surface of this cube. So the shear forces are forces acting parallel or tangent to the surface. So we can break that up into components. In general, it could be in any direction, of course, but we can break that force up into a component here in the z direction and a component in the x direction. Notice those 2 arrows on the face of this cube are aligned with the z-axis and the x-axis. So that's one possible thing that could be happening in the fluid surrounding this cube to exert a force on the surface of that cube. Now realize, in fluid statics, those shear forces are 0. I'm showing them here just as a reminder that in general that's possible, that there could be shear forces inside the fluid, but in the fluid statics section of the course, those forces are going to be set to 0. Now the other thing that could be happening on this face is there could be a normal force. So the fluid outside of the cube could be pushing perpendicular to that surface. And in fact, in fluid statics, that's the force that is much more important, because that force is due to the pressure in the fluid. Remember, pressure is a compressive stress in a fluid, so it's a normal force on any surface that we want to focus on in the fluid. Now also, as a reminder, remember that we've defined the pressure in the center of this cube to be P. So the normal forces on all of the faces are going to be dependent on the pressure being exerted on all 6 faces of this cube. So we're going to look at that in more detail now. So for a static fluid, or a fluid in rigid body motion, in other words, a fluid in a hydrostatic state, the shear forces are 0. So those red forces that I showed on the previous slide are gone. And the normal forces are due to pressure only. It turns out in fluid dynamics, viscosity actually also contributes to those normal forces. But in fluid statics, shear forces are 0, and the normal forces are due to pressure only. So we need to figure out how to express that net force on that little fluid element due to pressure. So what we're going to do is simplify that a little bit by just focusing on the y direction, just one direction first of all. And what's happening in the other 2 directions is very, very similar. So we'll focus on the y direction. So we'll have a little simplified sketch here. Rather than showing a 3D sketch of our little cube, we're just looking at it directly now. So we're just looking at the YZ face. So notice I still have my same coordinate system here. The x-axis is pointing straight out of the screen towards us. So Y will be this direction here, horizontal I'll call it, and then Z our vertical direction. And the size of this differential element, remember, in this direction is dy. So what we're going to do first of all is focus on what's happening on this face of the cube. And remember, we're still trying to figure out the surface forces, so we want to come up with an expression here that tells us the force that the fluid outside here is exerting on this face of this cube. And remember, this face of the cube is a little square. We're just looking at it edge on. So we're trying to figure out the magnitude of this force, first of all. Well, this is a pressure force. It's a normal force, and that normal force is due to pressure. Remember, the pressure at this location is P. So the question is, what is the pressure at this location? And the pressure at this location will be different than the pressure at this location, and how much different depends on the pressure gradient, so how the pressure is changing as we move from place to place in the fluid. So the pressure on the face of this cube, on the left face of this cube, will be P minus partial P partial y times dy over 2. I want to explain exactly where this is coming from. Now remember, this P here is the pressure at this location. But what we actually need is the pressure at that location. So we need to adjust or change that P a little bit. Well, how much do we need to change it by? Well, we need to subtract from that P this quantity. And we'll talk about why we're subtracting it here in a moment, but we just want to dig into this part and make sure we understand exactly what it means. Well, first of all, what do we see in here? There's two things in here. There's the rate of change of pressure with respect to y. So what does that tell us? Well, that tells us as we move in the y direction here, it doesn't matter which way we go, but as we move in the y direction, how is the pressure changing? So the rate of change of pressure in the y direction. Well, realize to get from here to here, we're moving in the negative y direction. So the pressure on this face is going to change as we move from there to there. How much is it going to change? Well, the rate of change of P in the y direction multiplied by the distance we travel. Well, realize the distance we travel is dy over 2 because we're going from the center to the left face. So the pressure change, this product here, the product of those two things, the rate at which the pressure is changing multiplied by the distance we move, that's a delta P. So we can call that delta P, the change in pressure as we move from here to here. Now, because we're moving in the negative y direction, we need a negative sign here in order to get the proper pressure on this face. So let's just see if this makes sense. Let's just say that the pressure gradient at this particular location in the fluid is positive. Okay, so I'm saying that partial P partial y is some positive number. Now what that means physically is we move from left to right, the pressure is increasing, right? Because we're moving in the positive y direction, so the pressure is increasing. So that means the pressure here is less than the pressure here. So that's why this negative sign is here, because this quantity in parentheses needs to be the pressure on this left face. So P minus partial P partial y times the distance dy over 2 is going to give us the pressure on the left face. So that's fine. So that, what we have so far here, is the pressure on this face. Now, it's not the pressure we want, it's the force we want. So we need to multiply that pressure by the area. And remember, the area of this face will be dz is this distance from there to there, that's the z coordinate, and dx is the distance in and out of the screen. So there's a little square there, and that's its area. So pressure times area gives the force. So the last thing we need to do here is give this the right direction, and the direction of this force is the positive j hat direction. So I'm just multiplying this scalar quantity by a unit vector in the positive j hat direction, because the fluid out here is pushing in that direction, the positive y direction. So that expression is the surface force, but only on one of the 6 faces of this cube. Now, if we look at the other side over here, almost exactly the same thing is happening. So there we have a pressure pushing to the left. So there are 2 differences between this expression and this one. First one, we see we have a positive sign here, so P plus partial p partial y times dy over 2. And that's because to get from here to here, we're moving in the positive y direction. So that sign is different there. And the other difference is this force is now in the negative j hat direction. So this sign, which was positive, becomes negative. So the only difference between these two expressions is those two signs. Now, this is a detailed look at what's happening in the y direction, but the same thing is happening in the z and the x direction, as we'll see. So bringing together these results, I'm going to take both of these results and add them together. So what we have here is our differential force, because we're only talking about a very, very small element of volume here. It's a surface force we're talking about, and right here we're talking just about the y component. So notice there's no vector quantity here. This is just the y component of that vector, which has 3 components in total, but this is just the y component. So all we're doing here is adding these two together. So here's the force on the left face minus the force on the right face to give the net force in the y direction. Now, if you take a look at this, notice that this p and this p cancel because of this negative sign right here. So they're both multiplied by dy dz, so that's the same. So that pressure and that pressure cancels. So this tells us something very important about these pressure forces. The pressure in the fluid actually doesn't matter. That does not determine what the net force is in the fluid. It's the pressure gradient, how the pressure is changing from one place to another, that is important, not the pressure itself. And that shows up mathematically here by those two p's canceling each other out. So the other thing we notice is we have minus partial p partial y times dy over 2 here. And we also have minus the same quantity here. So when we combine these together, they just become minus partial p partial y times dx dy dz. Notice the dy is here, and half times a half becomes 1. The 2 is gone, and the dx dz is common to both of these. So this is the scalar, or the y component of the force on that little control volume due to the pressure or surface forces. Now, we can do exactly the same thing in the other two directions. So if we went through this whole process in the x direction, we would get this, and notice it's exactly the same expression as this, except it depends on pressure gradients in the x direction instead of the y direction. All the rest of it is exactly the same, and likewise in the z direction, exactly the same expression again, except it's the pressure gradient in the z direction. So we now have all 3 components. That's our y component, this is our x component, and this is our z component. So we can bring those all together into a vector quantity again. So notice now we're still just talking about surface forces, but we're expressing force as a vector. So it's each of the 3 components we've got multiplied by their respective unit vectors to bring this all back into a vector. So what we're ready to do now is to combine all of these forces that we've identified back into Newton's second law. So we take what we've learned and we substitute it into Newton's second law. So we'll just break down where all of this is coming from. So notice the first line of this equation is all of these surface forces we've been talking about. So here's our surface force in the I direction, in the J direction, and in the K direction. So that's all of the surface forces, just written out in detail, so it's a little bit long. We add to that the body force that we talked about a moment ago. So this is the mass of the fluid in our control volume multiplied by G. So everything on the left-hand side of the equation here, remember, is a force acting on our differential element. The surface forces in the first line here, and the body forces in the second line. So all of that has to equal the mass times the acceleration. So that's the mass of our differential element, exactly the same quantity as here, but now multiplied by a, the acceleration of our differential element. So this is F equals ma for our differential element. Now notice what's happened here. Every one of the terms in this equation has dx, dy, dz in it. So one of the reasons this thing's so long is we have to rewrite dx, dy, dz 5 times. So we can divide this equation by dx, dy, dz and clean it up a lot. So dx, dy, dz canceled out. We have our pressure gradient in the I, j, and k hat directions. So remember, that's our surface forces. Here we have our body forces, and here we have our resulting acceleration. But because we've divided by the volume, these are now forces on a per unit volume basis, essentially, if we were to look at the units in this. Now, the very last thing we do here before we finish off our basic hydrostatic equation is we just use a little more compact notation for these surface forces. We have here the gradient of this scalar quantity in all 3 directions. So we can write this more compactly by using something called the vector gradient operator. So this operator, which we say as del, an inverted delta here, so this is the del operator, vector gradient operator. Notice it's not a quantity on itself, it's a expression that operates on or does something to another quantity. So the vector gradient operator is a vector, and its x component is the gradient of something with respect to x. Its y component is the gradient of that same thing with respect to y, and its k component is the gradient of that same thing with respect to z. So that's called the vector gradient operator. Well, notice what we have here is the vector gradient operator with a negative sign out front applied to pressure, because we have pressure in all 3 of these locations here. So a more compact way to write this is as follows. So the gradient of P, and that entire thing is a vector, is equal to rho times G minus A. So notice what we've done is we've moved this over to the other side of the equation because density is in both of those, and we factored the density out, and then we multiplied the whole equation by -1 as well. So these negative signs out front here are gone. This is positive pressure gradient is equal to rho G minus A. So this gives us the final form of our basic hydrostatic equation. So this equation is going to be the starting point for every problem that we do in the statics section of the course. And so let's just recap what it's telling us. Well, first of all, remember, this is just F equals ma. Sum of forces on our differential element of fluid is equal to its mass times its acceleration. That's what this equation is. But it's under a very specialized condition where the only surface forces acting on that fluid are due to pressure. So the pressure here is exerting forces on the fluid. Gravity is exerting forces on the fluid, and that results in some acceleration. This acceleration may be 0 in a lot of problems that we're going to do, but this is just 2 forces, surface forces and body forces, giving rise to acceleration potentially. Now, realize that this equation tells us something about the pressure gradient, right? If we figure out what all of these things are for a particular problem, that tells us what the pressure gradient is in the fluid. So it's fairly important to remember that the basic hydrostatic equation gives us information directly about the pressure gradient, not about the pressure itself. We're going to have to learn, when we apply this equation in different scenarios, how to get information about the pressure from an equation that directly tells us information about the pressure gradient. And so I'm going to be talking a lot about that when we apply this equation in different situations. But for now, this is the end of our development of the basic hydrostatic equation. And again, as I said, it's going to be the starting point for essentially every question that we do in this section of the course. So the next video, we're going to be taking this equation and applying it to manometers. So we can learn something about a very important tool in experimental fluid mechanics that allows us to measure pressures. So we'll take a look at manometers in the next video. See you there.